the start of the 1900s, atoms stopped looking like solid, unchangeable building blocks. Researchers studying mysterious rays from certain minerals found that some atoms changed on their own and gave off energy as they did. That process became known as radioactivity. It mattered for one simple reason. The energy released did not look like heat from burning fuel. It seemed to come from inside the atom itself. Then the picture of the atom sharpened. Experiments showed that almost all of an atom's mass sat in a tiny center, the nucleus, with electrons kept at a distance. That new nucleus was not just a detail of structure, it was a new place where nature stored energy. If chemical reactions only rearranged electrons, nuclear changes meant rewriting the atom's core, and that hinted at a far larger payoff than any ordinary fuel could provide. As scientists measured the particles and radiation coming out of radioactive decay, they kept running into the same surprise. A small amount of matter corresponded to a huge amount of energy. The numbers forced a new idea into view. Maybe the real energy frontier was not chemistry at all, but nuclear transformation. It was still unclear what changes were possible on purpose or how to control them. But the door had opened. By the 1920s, the big problem stayed brutally simple. Atomic nuclei carried positive charge, so they pushed each other away. That electrical repulsion rose fast as they got closer, like an invisible wall. Classical physics said the wall was too high. Even in the hottest stars people imagined, the nuclei should have bounced apart. Fusion looked like a good idea with no believable way to start. Then, quantum mechanics changed what impossible meant. In the new rules, particles did not behave like tiny hard balls with exact paths. They behaved like waves with chances. A particle could sometimes appear on the other side of a barrier without ever climbing over it. Physicists called it tunneling. It sounded strange, but it produced numbers, and those numbers could be checked against nature. In the late 1920s and into the 1930s, that tunneling idea got turned into a working tool. George Gamow showed how to calculate the odds that two charged nuclei slipped through the repulsion and reached the short-range nuclear force that pulled them together. The odds were small, but not zero. Fusion stopped being a fantasy. It became a rate, a temperature, a probability, something you could put into equations and test. By the late 1930s, the big question tightened to a single point. What kept the sun shining for billions of years? Burning coal could not. Gravitational squeezing could not last. The answer came from stellar physics, which treated the sun as a real place with measurable temperature and pressure at its core. In that crushing heat, hydrogen nuclei moved fast enough, often enough, that fusion stopped being a guess. Then the missing piece arrived, a step-by-step pathway that actually worked. Physicist Hans Bethe mapped the first full chain of reactions that turned hydrogen into helium and released energy in the process. In one route, the proton-proton chain, a rare first step, slowly started everything. Then later, steps ran more easily. In hotter stars, the carbon-nitrogen-oxygen cycle used heavier nuclei as helpers. What mattered was not just that fusion released energy, but that the numbers finally matched the sun. The reaction rates, the temperatures, the predicted power output. Stellar models lined up with what people observed. Fusion became a proven engine in nature, not an idea on paper, and it came with a blueprint, specific reactions in a specific order under specific conditions. The sun had served the evidence. In the 1940s, fusion stopped being only a process inside stars and became something people tried to trigger on Earth. World War II drove huge, secret nuclear programs built to turn new physics into usable weapons. Fission got there first. But planners already looked ahead, because fission explosions reached temperatures where lighter nuclei could begin to fuse. The idea shifted from theory to engineering pressure fast. After the war, that pressure did not disappear. It sharpened. The hydrogen bomb effort made fusion's promise brutally clear. If you could light it, the energy release scaled beyond anything chemical or even fission alone. Researchers learned which fuels mattered most, especially deuterium and tritium, and they learned what it took to start reactions: extreme heat, extreme density, and the right timing. Fusion showed its power, but only in a flash. The weapons race also left behind tools that did not stay in the weapons world. New national laboratories expanded, budgets followed, and measurement technology advanced quickly because designers needed to know what happened in microseconds inside violent experiments. Fast detectors, better vacuum systems, stronger magnets, and more capable computation spread outward. Those pieces quietly supported a new goal, using the same physics but stretching it from an instant of destruction into controlled, sustained fusion. In the 1950s, the challenge stopped being theory and became engineering with an attitude problem. Fusion needed a gas so hot it turned into plasma, and plasma did not like to sit still. The first strategy sounded simple. Squeeze it. In pinch machines, a strong electric current ran through the plasma, and the plasma's own magnetic field tightened like a noose, pushing it inward to raise temperature and density in one move. Another idea aimed for control instead of brute force. Physicist Lyman Spitzer proposed the stellarator, a twisted magnetic cage meant to guide charged particles around and around without relying on a single violent pulse. Either way, the hope stayed the same. Keep the heat in long enough for nuclei to collide and fuse. Then, the lab results delivered a surprise. The plasma refused to behave like a quiet fluid. It wrinkled, kinked, and slipped away. These were not small imperfections. As the pinches tightened, instabilities broke the smooth column into spirals and bulges, dumping energy into motion instead of temperature and sometimes touching the wall in an instant. Stellarators avoided some problems but revealed others. Particles still leaked, and turbulence scattered the heat. The new lesson landed hard. It was not enough to heat plasma to fusion temperatures. It had to be held there against its own restlessness. By the early 1960s, magnetic fusion looked stuck. The machines built in the 1950s leaked heat too fast, and instabilities kept tearing the plasma apart. Then a different layout gained attention in the Soviet Union. It wrapped the plasma in a donut-shaped chamber, but with a crucial twist: a strong, carefully balanced magnetic field that steered particles in tighter, more orderly paths. This approach became known as the tokamak. The surprise came in the numbers. Tokamaks held on to energy longer, and they reached higher temperatures than rival designs of the day. That mattered because fusion did not just need heat, it needed time at that heat. Better confinement meant the plasma stopped behaving like a sieve. For researchers who had spent a decade watching performance collapse as power increased, the tokamak results felt like a genuine shift in what was physically achievable. Once those results became known outside the Soviet program, the reaction turned fast and practical. Laboratories that had bet on other concepts began redesigning plans around tokamak geometry because it offered a clearer path to the conditions fusion required. The field's confidence changed with it. Instead of asking whether a controlled fusion plasma could ever be tamed, teams started asking what size, what magnets, and what engineering would be needed to turn that confinement into a reactor. In the 1970s, fusion no longer followed only one road. Magnetic machines kept trying to hold a thin, hot gas in place for long periods. But another idea gained momentum: inertial confinement. Instead of holding plasma steady, researchers tried to crush a tiny fuel pellet so fast that its own inertia kept it together just long enough to burn. It was a bold trade. Time became microscopic. Pressure became extreme. Lasers made that trade seem possible. As high-power laser systems improved, teams learned to deliver energy in short, intense pulses and to aim for a symmetrical implosion. The goal stayed simple to say and hard to do: compress the fuel, heat the center, and let fusion reactions race through before the pellet flew apart. This created a second, distinct pathway toward the same prize: ignition, a self-sustaining burst of fusion. With two approaches competing, the field needed one common scoreboard. The Lawson criterion filled that role. It tied success to a shared requirement: enough temperature, enough fuel density, and enough confinement time multiplied together. Magnetic confinement aimed for long time and moderate density. Inertial confinement aimed for huge density and vanishing time. Different machines, same yardstick, and it sharpened the question everyone chased: were they getting closer or only getting louder? In the 1980s, fusion research moved into an age of big machines, built to answer one blunt question: could the best ideas actually work at scale? Europe's joint European Torus, JET, led the charge, joined by other flagship tokamaks pushing higher temperatures and denser plasmas for longer pulses. The goal was no longer just proof of principle. It was performance, and performance demanded size, power, and extremely tight control. Then came the fuel that mattered most for a power plant: deuterium and tritium. It released far more energy than earlier test fuels, but it also brought new problems: radioactive handling, neutron damage, and strict limits on how the machine could run. When JET produced deuterium-tritium fusion power in the 1990s, it changed the mood overnight. Near break-even stopped being a slogan. It became a measured result. But the same experiments revealed an uncomfortable gap between a burst of success and a practical reactor. High performance arrived in peaks, not in steady economical operation. The plasma still flirted with instabilities, the walls still soaked up punishing heat, and the system still needed huge input power to hold everything together. Fusion looked possible in principle, even close in energy terms. Yet, as an everyday power source, it still refused to behave. In the 2000s, magnetic fusion entered a practical new phase because the magnets changed. Superconducting coils, cooled to very low temperatures, carried huge currents with far less wasted power. That let machines hold stronger magnetic fields for longer runs instead of short, expensive bursts. Stronger fields squeezed the plasma tighter, and tighter plasmas reached reactor-like conditions sooner. Progress still stayed hard, but the hardware finally began to match the ambition. At the same time, an older idea returned with better tools: the stellarator. Unlike tokamaks, it did not rely on a large plasma current, which meant it avoided some of the sudden instabilities that ended runs. The catch had always been its twisted, complex magnetic shape. In the 2010s, improved computing and manufacturing made that complexity buildable, and machines like Wendelstein's 7X tested whether careful design could deliver steady, high-quality confinement. Then the world tried to scale up. ITER, an international tokamak project in France, aimed to prove that fusion could produce far more power than it took to heat the plasma. It pushed engineering to the edge: giant superconducting magnets, remote handling, and a fuel cycle built around tritium. but ITER moved slowly, by necessity. That delay opened space for a new actor in the 2010s, private fusion startups that bet on smaller machines, faster iteration, and new magnet technology to reach results sooner. In the 2020s, fusion stopped sounding like a distant theory and started sounding like a series of measured, public milestones. In 2022, the US National Ignition Facility reported a shot where the fuel released more fusion energy than the laser energy that hit the target, then repeated and improved that result in later shots. It did not run like a power plant, but it changed what possible meant. At the same time, magnetic machines pushed hard on a different front: how long a plasma could stay hot, stable, and controlled. New superconducting magnets helped smaller devices aim for stronger fields, and record runs showed higher pressures and longer pulses than older designs managed. These were not headlines about electricity on the grid. They were proof of control moments where physics and engineering finally cooperated for minutes, not seconds. Yet commercial power still stayed out in front because a demonstration was not a reactor. The field still had to turn bursts into steady operation, protect walls from extreme heat, breed tritium fuel, and convert that heat into reliable electricity with high uptime. Even so, the contrast with the early era stayed sharp. Fusion no longer sat as a newly imagined nuclear idea. It stood as a set of sophisticated prototypes climbing measurable steps.